Welcome back to the channel. We start our Lecture 2 on Quantum Electrodynamics, QWD. Quantum electrodynamics also reshaped how scientists think about the relationship between mathematics and physical reality. In older theories, equations were often seen as tools that described behavior without necessarily reflecting what was truly happening in nature. In QED, the equations are more than descriptive. They encode the structure of interactions themselves. The symbols represent fields, particles, and symmetries that correspond to real physical processes. This tight connection between abstract mathematics and experimental results is one of the reasons QED is considered such a profound achievement. It demonstrates that the language of mathematics can capture features of the universe that are far removed from ordinary human experience. One of the most striking outcomes of QED is the idea that forces arise from particle exchange. This concept may sound simple, but it is deeply revolutionary. Instead of imagining forces as invisible strings pulling objects together or pushing them apart, QED describes them as the result of particles being emitted and absorbed. The electromagnetic force becomes the consequence of photons being exchanged between charged particles. This picture not only explains attraction and repulsion, but also provides a unified way to think about interactions across different physical systems. It suggests that what we call a force is actually a manifestation of an underlying quantum process. QED also introduces the concept of interaction strength through a quantity known as the coupling constant. For electromagnetism, this constant is related to the electric charge. Its small value explains why perturbation theory works so well in QED, and why calculations can be organized into a series of increasingly small corrections. Each additional step in the calculation corresponds to a process that is less likely to occur, such as the emission and reabsorption of extra photons, or the temporary creation of particle-antiparticle pairs. Because these processes are rare, their contributions are small, and the series converges. This mathematical structure is one of the reasons QED can achieve such high precision. At the same time, QED teaches us humility about the limits of prediction. Although the theory can calculate probabilities with extraordinary accuracy, it cannot predict the outcome of a single quantum event. When a photon hits an atom, QED can tell us the probability that the photon will be absorbed, scattered, or pass through unchanged. But it cannot say which of these will happen in a particular case. This randomness is not due to ignorance or experimental imperfection. It is built into the theory itself. Nature at the quantum level does not provide deterministic answers to every question. This probabilistic nature has philosophical implications that continue to be debated. Some interpret it as evidence that reality is fundamentally indeterminate, while others argue that there may be hidden variables or deeper levels of description yet to be discovered. QED does not settle these debates, but it provides a clear and consistent framework for making predictions. Its success suggests that any future theory must reproduce its results in the appropriate limits, just as QED reproduces classical electromagnetism when quantum effects are negligible. The conceptual richness of QED also lies in its treatment of time and causality. In calculations, particles can appear to travel backward in time, and interactions can involve processes that seem to violate ordinary causal order. These features arise naturally from the mathematical structure of the theory and from the requirement that it be consistent with relativity. While they do not imply actual violations of cause and effect in experiments, they challenge our intuitive understanding of how events unfold. QED thus forces us to expand our notions of time and process, showing that the microscopic world does not always conform to everyday expectations. Another important aspect of QED is its role in unifying different descriptions of light. Historically, light was sometimes treated as a wave and sometimes as a particle. QED resolves this duality by describing light as a quantum field whose excitations are photons. These photons exhibit both wave-like and particle-like behavior, depending on how they are observed. The same formalism explains interference patterns and discrete energy transfers, showing that these are not contradictory pictures, but complementary aspects of a deeper reality. In practical terms, QED has influenced the way experiments are designed and interpreted. Precision measurements in atomic physics, such as spectroscopy and magnetic resonance, rely on QED calculations to interpret their results. Without QED, it would be difficult to distinguish between effects due to electromagnetic interactions and those due to other forces or experimental imperfections. By providing a reliable theoretical baseline, QED allows scientists to search for tiny deviations that might signal new physics beyond the standard model. The theory also plays a role in understanding extreme conditions, such as those found in high-energy particle collisions or in the vicinity of compact astrophysical objects. In these environments, electromagnetic fields can become so intense that QED effects dominate the behavior of matter and radiation. Phenomena such as pair production, where photons transform into electron-positron pairs, and vacuum birefringence, where the polarization of light is altered by strong fields, are direct consequences of QED. These effects, once purely theoretical, are now being explored experimentally with powerful lasers and particle accelerators. From an educational standpoint, QED represents a turning point in how physics is taught. It emphasizes the importance of understanding interactions in terms of fundamental principles rather than relying solely on classical analogies. Students who learn QED are introduced to a worldview in which fields and particles are primary and forces are secondary effects. This shift in perspective helps prepare them for more advanced theories and encourages them to think critically about the assumptions underlying physical models. The elegance of QED also lies in its minimalism. With a small set of basic ingredients, fields, symmetries, and interaction rules, it accounts for a vast range of phenomena. This economy of explanation is one of the hallmarks of a successful scientific theory. It suggests that nature may be governed by simple principles that manifest themselves in complex ways. QED exemplifies this idea by showing how a single interaction, described by a single type of field coupling, can produce the rich behavior of electromagnetic phenomena observed in the laboratory and in the cosmos. Despite its achievements, QED leaves open important questions. It does not explain why the electron has the mass and charge it does, or why the electromagnetic interaction has its particular strength. These parameters must be measured experimentally and inserted into the theory by hand. This limitation motivates the search for deeper theories that might explain these values from more fundamental principles. In this sense, QED is both a triumph and a starting point, a model of success and a guide to what remains to be understood. The development of QED also illustrates the human side of science. It required creativity, persistence, and a willingness to challenge established ideas. The physicists who built the theory had to invent new mathematical techniques, reinterpret physical concepts, and confront paradoxes that seemed to threaten the consistency of their work. Their success shows how scientific progress often involves rethinking basic assumptions and finding new ways to connect theory with experiment. In the broader cultural context, QED has contributed to our understanding of what science can achieve. It demonstrates that even the most abstract aspects of reality can be described with precision and tested through observation. It also shows that scientific theories are not static but evolve over time as new data and ideas emerge. QED itself was refined and extended over decades, and it continues to be a subject of active research as physicists explore its implications in new regimes. Quantum electrodynamics also encourages us to think about the relationship between simplicity and complexity. On the one hand, the basic equations of the theory are compact and elegant. On the other hand, their consequences are extraordinarily rich and subtle. This duality reflects a common pattern in physics. Simple laws give rise to complex behavior. Understanding this pattern helps us appreciate why a theory like QED can be both mathematically beautiful and physically powerful. As we look toward the future, QED remains a cornerstone of modern physics. It provides a benchmark against which new theories are tested and a source of techniques that are applied across many fields. Its success gives confidence that the approach of quantum field theory is fundamentally sound. even if it must be modified or extended to incorporate gravity or to explain phenomena at even higher energies. In reflecting on QED, we are reminded that scientific understanding is built through a dialogue between ideas and evidence. The theory emerged from attempts to reconcile quantum mechanics with electromagnetism and was shaped by experimental discoveries that revealed inconsistencies in earlier models. Through careful reasoning and innovative thinking, these inconsistencies were resolved, leading to a theory that not only explained known phenomena but also predicted new ones. Ultimately, quantum electrodynamics offers a window into the deep structure of reality. It shows that the interaction between light and matter is governed by principles that are both subtle and precise. It reveals that empty space is not truly empty, that particles are inseparable from the fields they interact with, and that probability is a fundamental aspect of nature. These insights challenge our everyday intuitions, but they also enrich our understanding of the universe. By studying QED, we gain more than technical knowledge. We gain a new way of seeing the world. We learn to think in terms of processes rather than objects, of interactions rather than isolated entities. We see that the familiar phenomena of light, electricity, and magnetism are manifestations of deeper quantum laws, and we come to appreciate how human curiosity, guided by experiment and disciplined by mathematics, can uncover the hidden order behind the apparent chaos of the microscopic realm. Quantum electrodynamics stands as one of the great achievements of 20th century science, a theory that combines conceptual depth with empirical success. It continues to inspire physicists to explore the unknown and to seek ever more unified descriptions of nature. In doing so, it reminds us that the quest to understand the universe is not just about finding answers, but about developing new ways of asking questions and new languages in which to express them. Quantum electrodynamics also plays a subtle but crucial role in how we understand the stability of matter. At first glance, it may seem obvious that atoms exist and remain intact, but from a theoretical point of view, this stability is not trivial. The attraction between negatively charged electrons and the positively charged nucleus is explained by electromagnetic interaction. Yet without quantum principles, electrons would spiral into the nucleus, and atoms would collapse. QED refines this picture by explaining how electrons occupy stable quantum states and how their interaction with the electromagnetic field influences these states. The balance between attraction, quantum motion, and field fluctuations produces the stable atomic structures on which all chemistry and biology depend. One of the most remarkable consequences of QED is how it predicts tiny corrections to otherwise simple systems. These corrections are so small that they only become visible with extremely precise instruments, yet they are real and measurable. This tells us something profound about the nature of physical laws. Even when a system appears simple, there are hidden layers of complexity beneath the surface. For example, an electron in an atom does not merely orbit a nucleus under a simple Coulomb force. It also interacts with the quantum vacuum, with virtual photons, and with transient particle-antiparticle pairs. Each of these interactions leaves a minute imprint on the energy levels of the atom, producing effects that can be detected through spectroscopy. Another powerful idea that comes from QED is the notion that particles are not isolated objects, but rather excitations of underlying fields. The electron is not just a tiny charged dot, it is a manifestation of the electron field, and its properties emerge from how this field behaves and interacts with other fields. The photon is similarly an excitation of the electromagnetic field. This field-based view of reality suggests that what we normally think of as matter is deeply intertwined with the forces that act upon it. Matter and interaction are not separate categories, but different aspects of the same underlying framework. QED also provides insight into why light behaves the way it does in different materials. When light enters a medium such as glass or water, it slows down and changes direction. At a microscopic level, this behavior can be understood in terms of photons interacting with electrons in the atoms of the material. The photons are absorbed and re-emitted in complex ways that depend on the energy structure of the atoms. Although practical calculations often use simpler models, the fundamental explanation lies in QED, which describes how electromagnetic radiation interacts with charged particles at the quantum level. The theory further reveals that electromagnetic interactions are not limited to visible light. Radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays are all different manifestations of the same electromagnetic field, differing only in frequency and energy. QED treats all of these forms of radiation within a single framework, showing that the same basic interaction governs phenomena as diverse as radio communication and nuclear transitions. This unification of seemingly different phenomena is one of the hallmarks of a successful physical theory. Historically, the acceptance of QED marked a turning point in how physicists approached fundamental problems. Before its development, there was skepticism about whether quantum field theory could be made mathematically consistent. The appearance of infinities in calculations suggested that the approach might be flawed. The success of renormalization and the extraordinary agreement between theory and experiment changed this perception. It demonstrated that a theory could be both conceptually challenging and practically useful, provided it was handled with care and interpreted correctly. The intellectual style that grew out of QED also emphasized the importance of approximation and physical intuition. Rather than seeking exact solutions to complicated equations, physicists learned to identify the dominant contributions and to estimate the size of smaller effects. This pragmatic approach does not diminish the rigor of the theory. Instead, it makes it possible to connect abstract mathematics with real-world measurements. It encourages scientists to focus on what can be observed and tested, while still respecting the underlying theoretical structure. The work of Richard Feynman exemplified this balance between intuition and precision. His methods transformed complicated integrals into visual and conceptual tools that could be grasped more easily. These tools did not replace mathematics, but they provided a bridge between formal equations and physical understanding. As a result, QED became not just a technical theory, but also a way of thinking about interactions, processes, and probabilities. QED has also influenced the way we think about the future of physics. Its success suggests that unification and symmetry are powerful guiding principles. If electromagnetism can be described so precisely in terms of quantum fields and symmetries, perhaps other interactions can be described in similar ways. This idea has already borne fruit in the unification of electromagnetic and weak interactions, and continues to motivate research into grand unified theories and quantum gravity. The theory also highlights the role of experiments in shaping our understanding of nature. Many of the key features of QED, such as vacuum polarization and the anomalous magnetic moment, were revealed through careful measurements that exposed discrepancies with simpler theories. These discrepancies were not ignored. They were taken as clues pointing toward deeper principles. This interplay between experiment and theory shows how scientific knowledge advances through a combination of observation, creativity, and critical analysis. From a philosophical point of view, QED challenges us to rethink what we mean by reality. The particles and fields of the theory are not directly visible, yet their effects are measurable and predictable. Virtual particles in particular blur the line between what exists and what is merely a mathematical construct. They cannot be detected in isolation, but they influence measurable quantities. This raises questions about the status of theoretical entities and about how we should interpret the language of physics. QED does not provide simple answers, but it offers a framework in which such questions can be meaningfully discussed. Another lesson of QED is that nature does not always conform to our intuitive expectations. Concepts such as empty space, force, and particle have meanings in everyday language that differ from their meanings in quantum field theory. In QED, empty space is dynamic. Forces are mediated by particles, and particles are excitations of fields. Accepting these ideas requires a shift in perspective, but it also opens the door to a deeper and more coherent understanding of the physical world. As research continues, QED remains relevant in new contexts. Advances in laser technology, for example, are allowing scientists to probe regimes where electromagnetic fields are extremely strong and quantum effects dominate. In such conditions, predictions of QED can be tested in ways that were not possible in the past. These experiments not only confirm the theory but also explore its limits, searching for signs of new physics that might go beyond its scope. The enduring success of QED also teaches us something about the nature of scientific explanation. A good theory does more than fit data. It provides a coherent picture of how different phenomena are related. QED connects atomic spectra, particle scattering, and electromagnetic radiation within a single conceptual framework. It explains why these phenomena occur and how they depend on underlying principles such as symmetry and conservation laws. This explanatory power is as important as its numerical accuracy. In the end, quantum electrodynamics stands as a testament to the human capacity to understand the unseen. Through abstract reasoning and careful experimentation, physicists have uncovered the rules governing interactions that take place at scales far beyond direct perception. These rules may seem strange, but they are consistent and reliable, allowing us to predict outcomes with astonishing precision. QED shows that even the most subtle aspects of reality can be brought within the reach of human knowledge. When we look at the broader story of science, QED occupies a special place. It represents a moment when theory and experiment came together in an unprecedented way, producing a model of nature that is both elegant and exact. It also serves as a reminder that progress often comes from confronting difficulties rather than avoiding them. The infinities and paradoxes that once threatened the theory became the catalysts for new ideas and deeper understanding. Quantum electrodynamics continues to inspire both practical applications and philosophical reflection. It shapes our technologies, informs our experiments, and challenges our intuitions. It shows that light and matter, so familiar in everyday life, are governed by laws that are subtle, probabilistic, and deeply interconnected. By studying QED, we not only learn about electrons and photons, we learn about the structure of explanation itself, and about the ways in which human thought can penetrate the mysteries of the universe. Through QED, we see how a small set of principles can illuminate a vast range of phenomena. We see how abstract concepts become concrete predictions, and we see how the pursuit of understanding can transform our picture of reality. This is why quantum electrodynamics is not just a chapter in physics textbooks, but a cornerstone of modern science, a bridge between the visible world and the invisible processes that sustain it.